Okay, so here's another example for class 6 in dynamics. We have two blocks that are originally at rest. We're going to neglect the masses of pulleys and ignore any effect of friction on the pulleys, right? And we're ignoring the friction also between here, right? So that's kind of make it a little easier for us. We're going to determine the acceleration of each block, and we want to find the tension of the cable. So this is a very common type of scenario here where we have pulleys and cables and stuff. So we have dependent motion, and that's just great. So something we might want to do right from the start is find out some dependent motion things from this right here. So let me find from here, let's call this SA, that coordinate, and let's, we're going to do here you go, we'll start from right there, right? We'll assume that this thing never goes up any higher. So here's going to be our reference, and call that SB. So if we take the length of the rope, we could say that it's going to be SA plus 1, 2, 3 SB equal L. So we take the derivative, and so we happen to know that the B is going to be negative 1/3 acceleration A. Now, here is something I might not follow the same thing as all the other professors or the book. I don't quite like using the sign conventions right there because I seem to recall instances where it got frustrating that because I decided that was going to be positive and I decided that was going to be positive, and sometimes they agree with the other coordinate systems. So personally, I like to see what the arrangement's going to do, and just when it's time to put in replace because I want to reduce the number of unknowns, I'm just going to have that 1/3 relationship, and I'm going to make sure that I apply common sense to the thing as opposed to just putting in numbers. So now we have these two particles right here. We're still in particles. It's not rigid bodies, but we have an arrangement where there's two particles. And we're going to see that there's going to be a solution here. So first off, I'm going to start off with block A alone. And I will say that I have I just want to emphasize, I'm going to make an FBD and an IBD of it. So I go FBD, IBD, block equals block. And I'm going to cut the cord in order to do that right there. So cutting the cord exposes a tension. We also have weight. So here's the weight of A. We also have a normal force, which we call normal force. I'll call normal force A. Of course, there's only one normal force, but that's okay. Over here on the right-hand side, we're going to have the mass of A times the acceleration of A. We could say it's in the x direction, but there's nothing happening in the y direction. That thing's not, the block A is not flying off into space. So really, we just say that it's the acceleration of A. We don't have to really say it's in the x direction. So when we're done with this, we could say the sum of the forces in the x direction is equal to mass times acceleration in the x direction. We declare that being positive. So we write this out and say very simply that Ft is going to be mass of A times acceleration of A. And we really don't know anything more than that. We might put up here, by the way, that was equation 1. This is an equation 2. Now we're going to do for block B. And take the FBD and the IBD and draw it in there. Now, here we're going to have weight. I'm going to draw this coming down this way. This is going to be the weight of B. Upwards, we can include, let's cut the cables, all of them right there, right? So we have, here's the pulley, there's a tension there, there's a tension there in a cable, and there's a tension right there. So we're going to have FT, FT, and F, it's supposed to be an F, FT. No other forces are acting on this. I mean, it looks like there's a close gap there, but it's not rubbing up against the side, so fine. And it's not traveling left or right. It's only going to be, and we could actually kind of say, no, hopefully, it says that the thing is going down. And it's got to be going down. There's no friction down. There's no friction there, so it has to be going down. And so it is accelerating with a mass B times acceleration B downwards. So we take the sum of the forces in the y direction equals mass times acceleration in the y direction. We're treating upwards as positive because that's generally how we do the thing. And we take a look here and we say, oh, there's 3 of these. So 3 times Ft minus Wb, and that's it. Over on the left-hand side, it's going to be equal to a negative mb acceleration of b. And that's going to be equation 3. So what we have here is we have 3 unknowns. We don't know the tension, we don't know acceleration of b, and we don't know the acceleration of a. But we have 1, 2, 3 equations. 3 equations, 3 unknowns. We can do that. So we replace all of these things. So what I do is I take equation 1 and 2 and I put it into 3, right? So we're going to replace Ft right there, replace it with Ma and Aa, and then I'm going to replace my Ab with my with 1/3 Aa. And you can see why I didn't do replace it with the negative of the thing. Because I know it's the direction was decided by this right here. I'm not going to reverse the direction of this, of the motion of the thing. So I take 3 times MAAA right there. I've replaced that right in there. This, by the way, is going to be MB times G right there, because we are in SI units, and it's going to be equal to a negative MB times 1/3 AA. So 3 times 30 times AA minus 25, 9.81, it's going to be equal to minus 25, 1/3 AA. We can solve for the acceleration. And it ends up being 2.494, and these are meters per second squared. And so it's coming up this way right there. And if we want the acceleration of B, and by the way, I just drew an arrow so I can go ahead and make it vector. We want the acceleration of B, that's just going to be 1/3 2.494, or 0.8314 meters per second squared, which we can go ahead and say is downwards. Now lastly, we were asked for, so I guess we could solve all of those things right there. We could box those out. We were also asked for the force, the tension. What we could do is, easiest is just to put us back into here. So we'll say that Ft is equal to the mass of A, 30, times our 2.494. And that's going to be 74.82 newtons. And it's good to add that it's tension. Although we know it's going to be tension because you can't push a rope. and it is 10 o'clock at night, and I'm going home. Because I like going home. And that was a 10-minute example.